All right, what'd you guys come up with for y? Okay, about 28 degrees, right? Okay, so let's talk about how we do this. If y is what we're looking for, we have to go through and decide what we're going to name 8, 15, and 17, what sides those are, okay? So what do you call 8? That is the opposite side. What is 15? The adjacent. And 17 is the hypotenuse, okay? So when we're trying to find our angle, we have to know those two things. Okay, when I mean know, is that we have to have numerical values for the opposite side and the hypotenuse if we're going to use sine. We need to have numerical values for adjacent and hypotenuse if we're going to use cosine, and then opposite adjacent if we're going to use tangent. We have to have numerical values. Does that make sense? Okay. In this case, we have all three of those numbers, right? Okay. So we have a choice. If they would have just given us, let's say, those two sides, then you know adjacent and hypotenuse, and those are the only ones that you know, so you could not use something that has an O in it. So you would have to use cosine. Okay. But because we do know all three, we have a choice. Okay. So I'm gonna demonstrate here, just doing this with sine, and then I'll show you the other ones as well, but not as detailed of an explanation. So when I'm going to use sine, because I know I have the opposite and the hypotenuse, what I'm going to write is the sine. Remember what goes in the parentheses. Your angle that you are dealing with always goes in the parentheses. Okay. So if it's unknown, then the y goes there. If it is a known angle, then your numerical value will go there. But if you know a number for y, if that was like, say, 55 degrees, then you would have variables over here in the ratio. Okay? But our ratio is not going to have variables. Our ratio, for using sine right now, says we're going to use the opposite side and the hypotenuse. So I'm going to write this as 8/17. Okay. Now, that y is stuck inside those parentheses. You cannot just let the sign disappear or whatever. You have to do something to get that y to be by itself. Okay. And it's much like, I think we talked about this last week. If I have like x squared, or sorry, square root of x is equal to 8/17. To get that x out and the root to disappear, don't I have to square this sign? And then square that side, right? And I think we talked about the power of 2 and your root being inverses, right? They undo each other. Same thing on a much simpler base or basis. If I had something like this, these two things are being multiplied, right? 2 times x. To get that x by itself, I use the inverse of multiplication. So I divide both sides by 2. Same thing here. You have to use the inverse operation. It's just a little bit different because the inverse operation for sine is what we call sine inverse. Okay, so it's going to be that kind of notation. On the right-hand side then, you're going to do the sine inverse as well. And I usually run out of room when I do these problems. But this should look more like this. Let's get rid of. So you're going to have, so we had 8/17 here. And now I'm going to inverse this side, so it'll be sine inverse of 8/17. When you do this, we talked about last week, if I square a square root or I square root a power of 2, I'm just going to be left with the variable. Same thing happens here. Or down here, when I divided a product of 2 and x by 2, I'm just left with x, right? So when I inverse the sine function, I'm left, there's a cancellation that occurs there, and you're left with just y. On the right-hand side then, you're left with this. Okay? And that is the exact measurement of y. But if I told you to take sine inverse of 8/17 and go put it on a number line, you're going to have absolutely no idea where to put it on the number line. Does that make sense? Okay? So we have to use our calculator, and we're going to type in First, I have to make sure we're in the right mode, and mine's in degrees right now, so I'm good. And that just tells me I know that the answer that I get back should have a label of degrees. But you hit second sign, and then my 8/17, and it should give you that 28 that Landon gave. Okay. Now you can use cosine and tangent as well, right?
So it would work, that same process would work if we do cosine?
Yes, so if you're going to use cosine, so let's look at that picture real quick again. So cosine would be the adjacent and the hypotenuse, right? Okay, now a lot of people, so this math here actually gets overlooked a lot by students, and I've been in a lot of other teachers' classrooms and even seen teachers overlook this, okay? I think this math is important, especially knowing how much we use that in other courses, trig, college algebra, algebra 2 uses it a little bit. I think that's important to be able to understand that we're taking the inverse of something. Even if we don't ever, if you never see sine, cosine, and tangent again after this week, this idea of how inverses operate is the same idea how inverses operate here, same way that inverses operate here, and you will undoubtedly use inverses for the rest of your high school math careers, okay? So I think this math is important, but a lot of people will eventually say, oh, I'm looking for the angle. I know this is opposite and hypotenuse, so that's sine, so I just type in sine inverse of 8/17. So I'm just gonna kind of do that same thing to find cosine. So cosine is adjacent over hypotenuse, right? So when I type it in, I'm gonna go second cosine, adjacent divided by hypotenuse. And if we do this correctly, it should give me the same 28 number back. Okay. I can go tangent. Tangent is opposite over adjacent. So tangent would be 8/15. So it'd be tangent inverse of 8/15. And it gives you the same 28 back. So when they give you all three distances, it is your choice which one you use, sine inverse, cosine inverse, or tangent inverse, to generate the angle that we're interested in, okay? If they only gave you, and let's look at another one here real quick just to kind of compare. If they gave me this one here, okay, number 11, okay? What is 3 in comparison to y here? What side is it? That's opposite. And radical 34 is hypotenuse. So this is saying of these three things, which one do I have to use? I have to use the sine one, okay? So I would say sine of the angle that I identified opposite and hypotenuse, so sine of y, is equal to opposite over hypotenuse. And now, through the sine inverse, I would just look at that, evaluate it, and I've got my angle for y. So there I could not use tangent right away because I don't know what it is. Does that make sense? Okay. Now we could, once we know what y is, we can go find that adjacent side. Okay, I guess, I don't know that this would make a whole lot of sense to do, but we could actually find that right now, because could I use, that's a really big blue line. Do we know 3 and radical 34 are two sides of a right triangle? So when you have two sides of the right triangle, can you use the Pythagorean theorem to always find a third side? But here's my question. Do you want to go through, so okay, radical 34 squared is 34, 3 squared is 9. If I subtract those, it gives me 25, right? Okay, 34 minus 9. So this would be a length of 5. Okay, now just to kind of prove a point here, you could do all that work. The second sine of 3 divided by square root of 34. And I get 30.96, so that's what y is. Okay, but I could also say, well, once I find that 5, I could use tangent inverse, because opposite would be 3, adjacent would be 5. Does it give me the same number? That kind of makes sense? But, just think about it. Doesn't this make more sense to go that route? Because I didn't have to go and find 5 to do that. But you can if you want to. If you're a person that says, I always want to use tangent, there's probably procedures that are there available to you that will allow you to always use tangent, but you're going to have to do a little bit of legwork to get to that. I think it's just useful to use what they give you. Okay? Is it okay with everybody? One thing we talked about in the last class, and I think is important to discuss here as well, is that some of these questions that they give us are going to incorporate previous information. I think we're seeing that a lot in this course, that in order to solve for W and Z here, there are some things that we have to understand. Some markings, some notations that exist. Those markings tell me this triangle is what? What kind of triangle is that? It's an isosceles triangle, okay? Do you guys remember, and this is from chapter 4, if in an isosceles triangle, I take that segment, and if that segment ends up being perpendicular to the base of my isosceles triangle, so this 120 is my base. Do you guys remember what that red segment does to that 120? Cuts it in half. So that means W would have to be 60, right? Does that mean that would also be W is 60? So I cannot find Z if I don't know that. Okay? Once I know that, can I just essentially look at that image there to find Z? And if I do that, what side is Z compared to my 42? Opposite. And W, or the 60, would be the adjacent. So I'm going to say a tangent of 42 is equal to Z over 60. How would you solve for Z then? Multiply by 60. Is that what you're going to say? So 60 tangent 42 would be Z. And that should then give me that red segment. A lot of these guys, when I do these problems with you, I'm concerned about us getting into this point, okay? And then I'll leave it up to you to grab your calculator and evaluate that. Just make sure right now, whatever the angle was, whatever the unit was, in this case it's degrees, or whatever unit you want. So back up to that question 8 that we did at the beginning. Okay, they are wanting Y in this case to have a unit of degrees, right? So remember, that's what tells you what mode your calculator needs to be in. Okay, we're going to see a question here in a little bit that if you're in the wrong mode, it looks like an answer that would be acceptable. Sometimes if you're in the wrong mode, it gives you a completely ridiculous answer, okay? But other times, if you're in the wrong mode, it gives you an answer that might be acceptable. You might think is acceptable. So we just gotta pay attention to that. All right, I'm going to. So I sent it out a little bit ago. Part of this work, and you're not going to do the whole thing, but I've gone through and circled some of these questions that I want you to do in this worksheet for homework. What I want to get into today is section 8.4. Okay, now 8.4 is going to be new to us, but it's using a lot of the same stuff we've already been talking about, okay? So tonight's homework is not going to be directly over 8.4, okay? But talking about 8.4 today is going to revisit some of the stuff that tonight's homework is over. Does that make sense? Okay. Early on with 8.4, there's a lot of vocabulary and pictures and structures and things like that I want to make sure that we understand. It's just nice to get that stuff out of the way today, and then tomorrow we come to class and we can just hit example after example after example and develop the skill with this stuff. Bullet point there, not necessarily true for this class. This was from last year. Depending on where we're at later in the week, There might be a quiz, might not be. I'm just always, I'm always cautious at this time of year. I'm not saying that we're not going to have any more quizzes. I'm just cautious about using a lot of time in class because we're that window of available seat time to prepare for the end of course exam is narrowing, and I would much rather spend time discussing new material, developing skills with old material than wasting a day, not I won't say wasting a day, but using a day to test or quiz. Does that make sense? That being said, doesn't mean we're not going to have quizzes. Okay, they just might not be the traditional, full period quiz type thing if we have one. All right. Before we get into this stuff, when I was in school, Mr. Leidy used to say, we're going to do these application problems. We're going to do some applied mathematics, which basically means where in the real world can we use this? Okay, how can the average person go out and use this math? And you start seeing story problems. So I'll just give you a story problem. Now, they're going to make the story problems a little bit odd, okay, just to develop some skills here. But one of the main story problems that I hope that we can master is this one here. It says Oscar's in a lighthouse on a cliff, okay? He observes two sailboats, both due east of him. And it says the angles of depression of the two boats are 33 degrees, 87 degrees. Find the distance between the two sailboats. Okay, if the lighthouse is 803 feet off the sea level. You don't have to write that down or anything. I'll give that to you again when we actually do this problem. But we call that an applied question or an authentic question because there's real life stuff there, right? There's a person, there's a lighthouse, there's distances, sailboats. But at the same time, I think, is that really a application type problem? Okay, maybe you've seen them in like algebra, where let's say Hunter goes to the store and he buys 35 pounds of cashews and 47 pounds of peanuts and 3 pounds of walnuts, but he only has $28 to do it. Okay, does anybody go buy 35 pounds of cashews? No. So is it really an application problem? Okay, I always question these because I can see that there's real life stuff going on here. But is that legit? Is that something that people can do? Can we find measurements, okay, of angles like this, okay? And if I ask that question, the answer to that is much like, well, what if we talk about this distance here? Because in a lot of our problems, they give us distances, and we have to ask ourselves, well, how do I find a distance? What do we use to find distances? We have tools to do that, right? We use tape measures. We can use rulers, whatever, lasers, whatever we want to do to figure out distances. So there must be something that we can use to find these angles. And they're not common to the average everyday person, but these are the types of instruments that we can use to find angle measurements, okay? Some of these also kind of play a dual role and actually find distances for us too. But these are the types of instruments that throughout history we've used to find angle measurements, okay? Trigonometry actually started off in Greece as a tool for people to study astronomy. You guys know what astronomy is? What's astronomy? Okay, so investigating, learning things about the stars, about space, that kind of thing, right? Then they were interested in it for like human curiosity, but also for like creating calendars and planting seasons and harvest seasons and that kind of stuff, right? Being able to predict things based on positions of celestial objects. What happened then is that information, they developed tools that provided some angles, okay? And then that kind of parlayed itself into seafaring people using the same tools, okay? Because they use the stars to navigate, okay? This is called a sextant, which is what seafaring people like, Christopher Columbus, those types of navigators would use to make sure they know where they're at, okay? Some of those people were not good at using these. If you know anything about Christopher Columbus, he did not show up where he thought he was at, right? This is a device that or allows us to measure angles, okay? There's a lot of stuff going on with it, but that's kind of like one of the early tools, okay? These are what we call theodolites or diopters, okay? And you guys have seen people using these before, predominantly probably that one, okay? And you've probably seen them, let's go. Oh, if I could spell right, surveyors. You guys ever seen people out on the side of the road using those things? Okay, usually in construction sites, maybe the county engineers will go out before they do like a lane of like water pipes or sewage pipes or even constructions of roads. They will go out and take measurements of things, okay, using these types of devices to measure distance and to measure angles, okay. All of them have some type of eyepiece to them, and then there's going to be some type of, you can see it here, kind of a circular thing that is going to be somewhat of a protractor. Okay, this one's got it here. You can't see the one here. It might even be digital there. These are inclinometers or clinometers, okay? Kind of the same structure, okay? You got an eyepiece, you've got an angle that is being laid out on these protractors, and that's going to allow us to find angle measurements. So you might ask, well, that's not very common. You can find these in Menards and Lowe's, okay? You can buy these, they're usually right next to the tape measures, okay? A little bit more expensive. But you can make one out of a protractor. What we do with the protractor is we basically use, like a third grade type picture here, but you use the edge of your protractor and it's just got a straw taped to it to like model your eyepiece. But basically what you do is you just align your line of sight, your eyeballs, with the flat edge of your protractor. You take a string with a weight on it, and that weight is going to be constant all the way through. It's always going to, because of gravity, hang straight down, right? Okay, right to the core of the earth. When I move this, let's say I don't want to view my cursor up there in the top right-hand side of my screen, I would have to rotate this picture or rotate that protractor so that I could see my cursor through that straw. Does that make sense? Well, when I rotate that, that weight is still going to be positioned where it's at. It's still going to be hanging straight down. Does that make sense? But instead of going through 90, I'm going to look up at this X up here. That line will probably cross through maybe like 70. Does that make sense? The angle then from where I'm looking right now, so this would be, so if I look there, that would be kind of looking straight through the eyepiece as it is. If I rotate this and I look up, okay, my line of sight to that X up there is going to be kind of that dotted line, right? Does that make sense? This weight will pass, this string will pass through 70, and that 70 helps me get that 20. Okay, it's going to be that angle is always the complement of what this passes through. Just through a little bit of geometry and physics, we can transfer that value. That kind of makes sense? So if I want to look at something that is above me or below me, I could use a device like this. I can find out that angle to a certain level of precision. You guys talk about precision in science. Is that a very precise instrument? No. Am I going to be able to repeat that 20 degrees multiple times? Okay, it's probably not very accurate either, but it gets me in the ballpark. These things are much more precise and accurate, okay? Especially that one, because it involves lasers and all that kind of stuff, okay? Usually with that one, you'll see this second guy here with markings on a stick, and basically he's seeing those things through that eyepiece. Sometimes those things have like reflectors on them. And basically a laser is sent from this one, hits that one, comes back, and we know the speed of light. We know the speed that it took to hit that and come back, and using that little distance equals rate times time formula, we can actually find the distance between those two things by the speed of reflection for that laser. But those are devices that we can use to find distances and angle measurements that maybe make these problems seem a little bit more real, okay? Or that we could actually go outside and do them. If our math department had endless financial resources, we'd go buy some of those when we go outside and we measure trees and stuff like that with them. But we don't have, one of those things costs probably $150, so we're not gonna buy any. But as we do some problems, we do that problem with Oscar on the lighthouse. We're gonna need some terminology. If you look through these problems that we're gonna see in the next couple of days, they all have a consistent set of terminology that they use. Okay, these 5 vocabulary words are common. Okay, first one is horizontal. What's horizontal mean? Yep, left to right, correct? Left to right, slope of a line that is 0, right? Okay, so horizontal, usually when we're thinking horizontal in these aspects, we're talking about the ground. Okay, we're going to make the assumption that even though we're working sometimes with distances that are miles apart, we still make the argument that the ground is flat. Okay, if I'm trying to, if we're trying to find the height of one of those statues in the courtyard using shadows, well, we can say that when that shadow is cast on the ground, that is so short that we can make the assumption that the ground is flat. Okay, but there is a curvature to the earth, right? No matter what distance I choose, whether it's from here to Dixie Highway, there is a curvature that's experienced from that travel from here to there. Okay, that curvature is just so small that we're just gonna make the assumption it's flat. Okay, if I was traveling from here to, where'd you go on vacation? Orlando. Okay, if you were to drive that, you don't feel the curvature, but you actually travel, instead of a straight line, you're traveling an arc of the earth, right? We are going to be doing things on a small scale, so we make the assumption that every surface that they give us in these problems are horizontal. But it's any line constructed so that it's parallel with the horizon or another horizontal line. Okay. If you've ever been out in the country at night, you can maybe see, when you look at the horizon, you can actually see the curvature of the earth, right? At the ends of the horizon. We're going to work on a small enough distance to where we can say that line, that horizon, is always horizontal. We have a line of sight. So whatever you're looking at, whenever you are looking at something, if you were to connect your eyeballs to that thing with a line, that's your line of sight. Okay? A lot of these, most of these, with their term, try to tell you what the vocabulary, what the definition is. Okay? So the term tries to tell you what the definition is. Line of sight. Angle of elevation. What's elevation mean? Or what's elevate mean? You go up, right? Okay. So if my eyes right now, if I'm looking straight at my smartboard, but then I take my eyes and I look at the projector, my eyes elevated, right? Okay, or my line of sight elevated. When you are looking at something and your line of sight goes up, okay, so if you're trying to look at something essentially above the horizon, there is a line of sight that creates what we call an angle of elevation. Okay, so it says if the object being observed is above the horizontal, then the angle between the line of sight and the horizontal is called an angle of elevation. Okay, well, if I have an angle of elevation by looking up, I should have an angle of depression when I look down. Okay, angle of depression is looking down. I'm going to put an asterisk next to this one here. An angle of inclination. An angle of inclination, a lot of times authors will misuse this word. They will use it as a synonym for elevation. Okay, but basically what it means is an angle of incline. Does that make sense? So a lot of times, like picture of problems that we would see is, say we got let's say a flat land, but then it turns into a hillside. And on that hillside, maybe we've got some trees. And I want to find maybe the height of that tree based off the shadow of that tree. Well, what they will do is they'll tell you that hill is at a certain angle of inclination, which would be essentially, if we take that line, that horizontal, and kept tracing it out, that's your angle of inclination. Does that make sense? Which is the idea that if you were laying on your stomach down here at the bottom of the hill, so my stick figure laying on their stomach, and you looked at the base of this tree, would your line of sight actually follow that hillside? Does that make sense? So that's what they're talking about when the line of sight follows a physical object. Your line of sight follows that hillside. Another one is like the common one you see is Landon's outside, flying his kite. Okay. The angle of inclination. Okay, so my string on my kite is essentially it plays a double role as being the line of inclination or the line of sight, but that because if you're looking down your string here for your kite, your eyesight, your line of sight would be following that physical object of the string, right? Does that make sense? So this would be your angle of inclination right there. But again, like I said, they get misused sometimes, but we can treat them the same way, even though they get misused. So just want you to be on the lookout for that. We've done this in the past, and I've given people these 4 vocabulary words, and then in, of course, exam or math Excel, we'll throw that one in, and people's minds explode. Okay, so put it in there. Make sure we understand that you can treat these 2 the same way. Every picture that we come across, whether it be, I don't care what the context is. I don't care if it's a person in a truck looking at the top of a building. I don't care if it's somebody in a hot air balloon looking down the ground. I don't care if it's someone in an airplane looking down at a sailboat, okay? Whatever it may be, you can always break the picture, the scenario, down to a picture such as this, okay? Which ultimately here, I'm gonna put this line in right here. That line right there would be the same as that one there. Does that make sense? Okay. Do you guys see a rectangle here? Okay. Every picture is going to break down essentially to that rectangle. But if we go through any of these problems, and we'll see the first one here in a little bit, if you're a person that is sitting in this truck, if you are in the truck and you're gonna look at the top of this building, your line of sight is that dotted line, correct? Okay. The ground is horizontal. So if we go back up to the definitions, it says if you had a line of sight and a horizontal intersecting, they create what we call our angle of elevation. And think about this. If you're in this car and you're driving normally, you'd be probably looking that direction, right? But if you change your eyes and you look up here at that, don't they have to elevate? And they elevate by that angle, okay? This picture also provides then the scenario, the situation where we could actually be standing up here. We're on the flagpole or next to it, and we're looking at this person in the truck, okay? When we do that, the picture that you're gonna see most of the time is that line is not going to be there, okay? And if they want, so they say, you are a person standing on the building, but your angle of depression to the truck is, let's say, 35 degrees. In order to actually implant that, because look at what the definition of angle of depression says, object is being observed is below the horizontal. Well, I don't have a horizontal here. You have to put one in. You have to draw one in. All horizontals are parallel, okay? So the angle created by this horizontal in my line of sight, that angle right there, what would you say that it is compared to that one right there? Alternate interior. So your line of sight is a transversal. Okay, so you're going to start seeing things from chapter 3 being revisited here. Okay, a lot of stuff going on. We got angle stuff from chapter 8. We've got we're going to use sine, cosine, and tangent from chapter 8. We've got angles of depression that came from chapter 3 with transversals. We've got rectangles here, came from chapter 6. A lot of stuff from previous sections going to be incorporated in these types of problems. Okay, once you get a picture though, these things are not that difficult. Okay, so I just want to do one example and then we'll pick up from here tomorrow. What I find people to struggle with is reading. Okay, just being able to read and comprehend what they're talking about. Okay, I like to take these questions, I like to read them once and then take them apart sentence by sentence. So it says an observer on the first floor of an airport control tower sights an airplane at an angle of elevation of 32 degrees. The pilot reports the plane's altitude is 3.5 kilometers. What is the plane's horizontal ground distance from the tower? Okay, so going sentence by sentence. There's an observer on the first floor of an airport control tower. Okay, towers are on the ground, right? So I'm going to draw my ground. Here's my tower. Okay, there's a person in there, and they sight an airplane. Airplanes are going to be where? In the sky. So there's my airplane, right? They sight them. So that means they're looking at them, right? So what would that line right there be from my observer's eyes to the airplane? That's your line of sight. Your line of sight, what? So if that's my line of sight, just say L of S. What is this purple line? What's that called? Your horizontal. What angle is made by the intersection of a line of sight in a horizontal? Angle of elevation. So there's telling you that that is 32 degrees. Does that kind of make sense? Altitude. In maybe this context, most people are thinking altitude is what? How would you refer to altitude?
The height.
The height. How far this guy's off the ground, right? Okay. Now, if I'm thinking about geometry, that is appropriate as well, because that is the leg of a right triangle, correct? And legs of right triangles are altitudes for the triangle. Okay. So we get that information. Okay. So the things that I don't have here in the problem numerically given are my line of sight. So I'm just going to call that Y right now. And my distance from here to there, which I'm going to call X, right? Those would be the parts of my triangle. Does that make sense to everybody? So every one of these, we're going to try to create one of these triangles. Which one of those would you guys maybe most appropriately identify as the ground distance, X or Y? X, okay? So when they say horizontal ground distance, they're looking for us to find X, okay? If they just said, what is the distance between the person and the plane, that would be Y. Does that make sense? But because they add the adjectives here, horizontal ground to distance, we know we're looking for X. So now here's my question. If I've got that angle, can I name my sides of my triangle off that angle? What would this 3.5 be? Opposite. What would X be? Adjacent. Which trig ratio uses opposite and adjacent? Tangent. So I'm going to say tangent of 32 degrees is equal to opposite, which is 3.5, over adjacent, which is X, right? Okay. Once we get the picture, and this is something I'll commonly do on my own, is that I'll take all like the graphics out, I'll take the airplane out, take the tower out, and it just looks like a picture from 8.2, right? It looks like just like Math Excel was giving us those basic pictures like at the beginning of class today. If I multiply both sides by my denominator here, so multiply by X, multiply by X, those are going to cancel, right? So you get X, tangent of 32 is equal to 3.5. Now what do I need to do? How do I solve for X here? Divide both sides by tangent of 32. That's my coefficient. So I'll take 3.5 divided by tangent of 32. Now 32, what was the label for that 32? The label was degrees, wasn't it? Okay. So when I grab my calculator, what mode should I be in? degrees, okay? I'm going to do this. So when I open Desmos is by default, at least this right now, if you get on their website and open it, it's by default in radians. And if I type 3.5 divided by tangent 32, and I don't pay attention that I'm in radians, and it doesn't even show up here, okay? Doesn't remind me that I'm in radians, I get a number here, 5.29. Now think about this. If this airplane was off the ground at 3.5 miles or kilometers, does a distance of 5.29 for that distance, does that seem somewhat appropriate? It's not ridiculous, right? It's not like 10,000 or it's not negative. It seems like that could be legitimate for that distance. So I could write that, type that into Math Excel, and it'd be wrong even though it seemed right. 5.29, if I change the degrees, look what it changes to. 5.6, that's the actual distance. Does that make sense to everybody? Sometimes if you're in the wrong mode, your answers are going to be ridiculous. But sometimes when you're in the wrong mode, your answers are actually pretty close to what the actual answer is. It's just based on what a radian is, which I'll talk about maybe a little bit tomorrow. Yes?
Could you also use y here? If you didn't want to use x, you can use hypotenuse.
Yeah, but that's going to, so if I want to find y, so remember the question said what's the ground distance, right? So I could find y, but that's not going to be that distance. But you could find y, then use that. So you have, once you found y, you have that distance, you use the diagram there and find x. But the quickest way to find that ground distance is to use tangent. So your homework, guys, is in an email.